this video, we're going to go over circles test number 5. So in number 1, we have a cyclic quadrilateral, and that means it is a quadrilateral inscribed inside a circle. And in a cyclic quadrilateral, the opposite angles are supplementary. So that means this angle and this angle will be supplementary. So 110 plus whatever that other angle is equals to 180 degrees. And the same thing with these two opposite angles. 72 plus whatever that angle is equals to 180 degrees. Now we need this one over here, so I'm going to focus on this equation. So on my calculator, I'm going to solve the equation by doing 180 minus 72, and I get 108 for the angle that we are looking for. In number 2, we have some parallel chords, and it does tell us that the measure of arc CD is 130 degrees. Now, we have a theorem that says parallel chords intercept congruent arcs. So the arcs between the parallel chords are congruent. AOB is a diameter. It says that in the question, and it passes through the center of the circle O. So that means from A to B this way is 180 degrees. It's a semicircle, half of a circle. So a total circle is 360 degrees. So we already have 180 and 130. If I add those together, we get 310. So that means if I do 360 minus 310, that means there are 50 degrees left in the circle. And since each of these arcs are the same, each of these has to be half of 50, which is 25 degrees. In number 3, we have a diameter that is perpendicular to chord CD. That means it forms 90-degree angles where it intersects the chord. We have a special theorem that says when a diameter is perpendicular to a chord, it actually bisects that chord into two equal parts. Whatever the measurement of CE is, the measurement of ED will be the same thing because it's split equally into two congruent parts. In the question, they also tell us that OA is 6 and that OE is 2. And notice how OA is a radius. It goes from the center of the circle to a point on the circle. All radii of a circle are congruent. So from O to B, there's the same measurement of 6 from O to B. We already have the 2-part OE. So that means EB has to be 4 in order to make 6. Once again, all radii of a circle are congruent. If this radius is 6, then this radius has to have a total of 6 as well. So now we're going to find the length of CE, which is one of the segments, the chord. Whenever we have intersecting chords, whenever you see that letter X, and we need to find a segment length, we're going to use our special theorem, part times part equals to part times part. So part times part is from one chord, each of the pieces. Part times part is from the other chord. And the diameter is a chord. It's just a special chord that passes through the center of the circle. So let's start with chord CD. The way that you find the pieces is where the two chords intersect, where that letter X intersects. From C to E is one piece, and from E to D is the other piece. So each of the parts is X and X. Now let's do chord AB, which is diameter AB. Once again, the way you find the pieces is from the intersection point of the two chords from the intersection of that letter X. So one piece is from E to B, which is 4. And then the other piece is from this intersection to point A, which is 8. It's the 2-part and the 6-part, which is 8. So we have x squared is equal to 32. We have x is equal to radical 32. And we do need to simplify the radical. So it is a multiple choice question. So one thing you can do is you can put radical 32 in your calculator, see what the decimal approximation is, And you can put the answer choices into your calculator and see which one has the same approximate decimal. Or if you know how to simplify radicals, either by hand or on the calculator, you can definitely do that. You can look for the largest perfect square that goes evenly into 32. And that is 16 and 2. The square root of 16 is 4. So we have 4 radical 2. For number 4, what we need to do in order to find the center and the radius is we need to convert the equation that we're given into the format that we're used to seeing, x minus h squared plus y minus k squared equals to r squared, so that we can clearly see what the center and the radius is from the equation. In order to do that, we need to group the x and y terms together, and we need to move the constant to the other side of the equal sign. So let me group the x terms together. So that's x squared and minus 4x. And I'm going to put a little box to indicate we're going to be finding the number that completes the square. For the x terms, I'm going to group the y terms together. That's y squared and 8y. And once again, I'm going to put a little box to indicate I'm going to be finding the number that goes there. I'm moving 11 over to the other side. So it's going to become a negative 11. And I also like to put the 2 boxes here as well to indicate to myself that whatever I add to one side of my equation, I also have to add to the other side of my equation. So the way that you find what number goes in the box is by using the formula b over 2 squared. A, B, C we don't have. A, B, C we don't have. So for the x terms, the b coefficient's negative 4. That is negative 2 squared, which is 4. The next step is that we are going to have to factor the x terms. And after you complete the square, the nice thing is it always factors to the same factor repeated twice. And the easy trick, if you don't remember how to factor for what goes next to the x, is your b over 2 before you squared it. So here, my b over 2 before I squared it was a negative 2. And that's what this is going to factor to. Okay, now I have to find the number that completes the square for my y terms. The b coefficient for my y terms is 8. So b over 2 squared would be 8 over 2 squared. That's 4 squared, which is 16. And now I just have to find what this factors to. Once again, after we complete the square, it's the same factor repeated twice. Find out what goes next to the y. If you don't remember how to factor, it's the b over 2 before you squared it, which here is positive 4. And then let me take a second and add up the stuff on the right-hand side of the equal sign. We had 16 and 4, which is 20. And negative 11. 20 plus negative 11 is 9. So now we have our equation of the circle in the correct format. And now let's pull out the center and the radius. Remember, in the equation of a circle, there's that built-in minus. So that changes the signs of the center. So in the equation of the circle, if you see a minus 2, that means that it really was a plus 2 to begin with because that built-in minus changed the plus to a minus. If you see a plus 4 in the circle equation, that means it was actually a minus to begin with because the built-in minus and the original minus made a plus. Minus and minus makes a plus. So in the circle equation, when you're pulling out your center, and let me label that here center, it is the opposite signs from what you see in the equation. And remember, on the right-hand side, this is not r, this is r squared. So in order to find r, you have to do radical 9. And radical 9 is simply just 3. So that is answer choice number 1. We're told that angle BAC is 70 degrees. And that's an inscribed angle. Inscribed angles are half of the arcs. So the arc BC is 140 degrees. Since AOB is a diameter, from B to C to A is 180 degrees. Since BC is already 140, C to A must be 40 in order to make the 180. Over here, we are given the area of the shaded sector. So this is a sector area question. I'm going to write my proportion sector area over here as soon as I identify that I'm working with sector area. My proportion is central angle over 360 degrees, assuming I'm working in degrees. And I do see the answer choices have degrees, so I think we're good with degrees. But the only difference would be if we were working with radians is we would change this 360 degrees to 2 pi, because 2 pi is the equivalent of 360 degrees, but in radians. 2 pi radians is the same as 360 degrees. And then on the other side, we have sector area. Sector area over area of the whole circle. And you can think of this proportion as part over whole because a central angle, one central angle of a circle is a part of all the central angles of the entire circle. So part over whole equals part over whole. Because the area of a slice of a circle, the area of a sector, is a part of the entire area of the whole circle. So again, you can think of this proportion as part over whole equals to part over whole. And see what we have that we can plug in. We have the sector area. They give it to us. They tell us that the area of the shaded sector is 2 pi. So in my proportion, I can plug in the sector area. That's 2 pi. They next tell me that the length of NL is 6. NL is a diameter of the circle. So that means the radius OL or ON, any radius of the circle, would be half of 6, which would make it 3. So now I can find the area of the whole circle, because remember, area of a circle is pi r squared. If the radius of the circle is 3, 3 squared is 9. So the area of the entire circle with a radius of 3 is 9 pi. 360, because the angle that we're looking for is going to be in degrees because the answer choices are all in degrees. But I need the central angle. Now be careful. It's asking what is angle n. Angle n is not a central angle. Angle n is an inscribed angle. For the shaded sector that they give us the area of, this is the central angle with the angle's vertex on the center of the circle. So in order to find what we're actually looking for, angle m, first, we're going to have to find the central angle because that's all we can find. So first we're going to find, so I'm going to label that as x. We don't have it. That's what I'm finding, the central angle. Let's cross multiply. We have 9 pi x equals 2. 360 times 2 is 720. 720 pi. We get the x by itself by dividing both sides by 9 pi. The pi's cancel out because there's pi in the top and the bottom. And now all I have to do is 720 divided by 9, which is 80. So the central angle here is 80 degrees. And remember, central angles are equal in measure to their intercepted arcs. And notice how the angle that we're looking for, angle M, also intercepts arc ML. And inscribed angles are half their intercepted arcs. So angle N would be 40 degrees. Over here, notice in the previous example, we have a letter X. And what we're dealing with here again is segment lengths, because we need to find the length of CE. They do tell us that chord AB bisects chord CD at point E. So that means if chord CD is getting bisected, it's being split into 2 parts. So we could call this piece X as well, because these are the same if chord CD is getting bisected. And now we can use our term earlier in the video for finding segment lengths in chords. Part equals part. So chord CD from the point of the letter X to the other end is X, and X And from the intersection point on the other chord, that's 9 and 8. So we have x squared is equal to 72. X is radical 72. It does say in simplest radical form. So you will lose a point if it's not in simplest radical form. You can either use your calculator to do that, or if you know how to simplify it by hand. For many of you using the calculator, I saw a lot of people getting this 3 radical 8. That's not the simplest form. So on your calculator, if you're using your table of values and you find whole numbers, make sure you scroll down to the last whole numbers that happen. If whole numbers occur multiple times, that means that those are steps along the way to fully simplifying it. But the fully simplest form would be the last time that you see whole numbers if you're using the calculator trick. Radical 72, the largest perfect square that goes into it is 36, 2 times. So that is 6 radical 2. Over here, what we need to remember is that 2 tangents that come out of the same opposite point, the same circle, are congruent to each other. So here, this tangent and this tangent to circle y come out of the same point t, so they're congruent to each other. If we look at the longer tangents to circle x, this one and this one, they come out of the same point t, and they're both tangent to the same circle x. So they're congruent to each other as well. They tell us that the ratio of TA to AC is 1 to 3. So TA is the 1x part of the ratio because it's written first, and AC is the 3x part of the ratio because it's written second. And we know that TS is 24. So that means TC also has to be 24. So we can make an equation, 3x plus 1x equals to 24. 4x equals to 24. X is equal to 6. Be careful, that's AT or ET. These are the 1x parts. We're looking for SE, which is the 3x part. So you do need to take 6 and multiply it by 3 in order to get the length of SE, which is 18. Make sure you clearly label your answers as well. Over here, we needed to determine if the point lies on the circle. So first I'm going to do it not graphically, and then I'm going to do it graphically and talk about what people might have done incorrectly. So not graphically, I'm just going to write the equation of the circle. The center is 0, 0. So that's squared plus y squared because remember, this is the format for the equation of a circle. So if it's minus 0, that's the same thing as x squared plus y squared. And equals to radius squared. The radius is 5, so radius squared is 25. The point is 5, negative 2. So let me plug in the x coordinate for x. Let me plug in the y coordinate for y. And let me see if this checks out. 25 plus 4. And nope, this does not check out. So the answer is no. It's not an explanation question, so if you have this work, it's enough to justify it. The point does not lie on the circle. If you were doing this graphically, you could make your own XY coordinate grid. And the center of the circle would be at 0, 0. And the radius is 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now the issue is a lot of people were being very messy with making their circles. You have a compass, so just use a compass. And it could be, let me try that one more time. It could be inaccurate if you graph your circle messy and you're doing this graphically. 1, 2, 3, 4, 5. 1, 2. See? Mine's messy. It looks like the point on the circle, but it's actually not. Try to do this a bit neater so that we could see it. It's hard on the computer. Oh, see, it keeps moving on me. And now you can see that point is not actually on the circle. So once again, graphs are hard if we make our graph a little bit messy. So the way on the left is the easy way that you can make sure you get the answer right. using the circle equation. Okay, over here we have some outside segments. We have a secant and a tangent to a circle. We're told that CA, which is the whole secant, is 12.5. People were getting confused because of their labeling. Make sure you label in a way that you do not get confused. And CB is 4.5. Determine and state the length of DA. So when we're dealing with segment lengths of outside segments, whether it's tangents, secants, or a combination of both like we have here, the theorem that we use is whole times outside equals whole times outside. So for the secant, we already have the whole. The whole is already 12.5. We do not have the outside part. The outside part is BA, the part outside the circle. What you can do is 12.5 minus 4.5 and get the outside part, which is 8. And then for the tangent, the whole tangent is x. And since the tangent is entirely outside the circle, the outside part is the same thing as a whole whenever you do have a tangent. So I'm going to do 12.5 times 8, and I got 100. And it's nice when the numbers work out nice. And if we take the square root of both sides, x is equal to 10. And x is what we're finding. We represented dA as x. 10 is the answer here. Over here, we're going to talk about this proof. So for this proof, the first thing that I'm going to do is mark my diagram. And as I'm reading that chord BC is parallel to secant ADE. A lot of people don't mark parallel lines in their proof. I'm not really sure why, because that's why a lot of people are missing things in their proof. So whenever you have parallel lines cut by a transversal, look for angle relationships. And I'm highlighting my letter Z so you can see it clearly. And whenever you have a letter Z, that means you have alternate interior angles. In the corners of your letter Z are congruent alternate interior angles due to the parallel lines. Inside the lines, on opposite sides of the transversal, alternate interior angles. Okay. I don't know what my goal is, but I found those alternate interior angles that might be helpful. So let me take a look at my proof statement. In my proof statement, I see that I'm proving a proportion. So now I'm going to ask myself, how do I know when things are proportional? Well, I know that corresponding sides of similar triangles are proportional. So what we're going to be doing here is we are doing a similar triangle proof. First, we're going to prove two triangles similar. And then after we prove them similar, we can prove the proportion. We are going to be using AA to prove similarity. You always use AA in two-column proofs to prove similarity because for SAS and SSS, for similar triangles, that means sides are proportional. And if you don't have numbers, it can often be impossible to show that sides are proportional. So our proof is going to tell us which triangles to focus on. So here there are only two triangles, but I do want to review using the proof statement to figure out what triangles you're focusing on. A lot of times you have more than two triangles in the question. So BC is the first segment I see. It's from that top triangle. And then we have CA and AB. I see AB is from this triangle as well. So already I see we're dealing with this triangle. And then we get CA. I kind of put that on hold. So CA is from the bottom triangle and from the top one, but it's from the bottom one as well. And EC. So from our segments here, we have our two triangles that we're focusing on. Okay. From here, let's look for stuff that we can use. We already have one pair of congruent angles for AA from the alternate interior angles. I'm going to look for other circle angles that I know. I like to always look for inscribed and central angles when we do have a circle. Now, we don't have any central angles here. If I take a look at center O, there's nothing really, there's no angles on that. But I do see some inscribed angles. Specifically, I want to take a look at this inscribed angle over here, inscribed angle ABC. Notice how angle ABC is an inscribed angle, and if you follow the ends of its rays, one goes to A and one goes to C. So it's an inscribed angle that intercepts the diameter. Since it intercepts the diameter, let's just go through why. It's a right angle. Let's talk about why. AC, the arc, is 180 degrees since the diameter makes it a semicircle. And since inscribed angles are half of their intercepted arcs, if arc AC is 180, half of that would be angle ABC, which is 90 degrees. So this is a 90-degree angle over here. Now, if we can find another 90-degree angle in the other triangle, then we are good to go. I have to see where that is going to come from. Well, in this one, it's pretty simple to see because what we have here is a radius or a diameter, same thing, because, radius is just half of a diameter. We have a radius and a tangent to the circle that intersect. A radius and a tangent to a circle are perpendicular to each other where they meet. That means they form a right angle because perpendicular lines form right angles. And now we have our second pair of angles for AA. After we prove the triangle similar by AA, then it's one more step to prove the proportion. The reason for proving a proportion is the same reason every time. Corresponding sides of similar triangles are proportional. That's how we're able to make a proportion. I'm going to pause the video and I'm going to write this proof up and then I will unpause. And here is the completed proof. Feel free to pause the video so you can take a look through it. I'm going to switch over to the next question now. The last question is to construct a regular hexagon. So in order to do that, the first thing I'm going to do, just so you could see what I'm doing, is I'm going to just make the radius of the circle. And I should say that my construction, since I'm doing it on the computer, is not going to be super, super accurate. Oops. One second. But I am going to try to be as accurate as possible, but it's hard on the computer. So I'm going to open up the length of the radius as best as I can. And as I said, this is very hard to do on the computer, and I'm just going to measure that length. I'm going to put my compass over to that point where the radius intersects the circumference of the circle. And using the length of the radius that we just measured, I'm just going to make an arc that intersects the circle. And then I'm going to move my compass over to that intersection point as accurately as I can. Oops, as we can see, that was not accurate. Let me put it on that point. And then using the same length of the radius, I'm going to make another arc, and I'm going to keep doing this. I'm going to intersect. Once again, this is all without changing the length of the radius, the length of the compass, which is the distance of the radius. Just got to intersect the circle. And this should occur 6 times. And on the 6th time, which I'm about to do right now, you should end up, if you are being super accurate, you should end up exactly intersecting the point where you started. And as you can see, mine's a tiny bit off. Let me redo that. Okay, so as you can see here, if you are super accurate, it should line up. Now, all we're going to do is we are going to take our straight edge. Let me get a different color. Oh, there we go. And all of those points where my arc intersected the circle, I'm just going to take those points and I'm just going to connect them together. And what I should get here is an equilateral hexagon. Once again, mine's not 100% accurate because I did it on the computer. It's a little bit hard to do this on the computer, so it's not 100% accurate. Yours will look you do it on paper. In order to answer the second part, make sure to label your hexagon according to the question. A, B, C, D, E, F. And in part B, it says to connect chords FB and FC. I just connected that so bad. Let me do that one more time. And sorry, mine is not super accurate, as I said, because of my construction with my compass, not super accurate. It should line up over here on yours. There we go. Mine just not super accurate because I was using the computer compass. And it's asking, according to the angles, what kind of triangle is triangle FBC? What type of triangle, according to its angles, would FBC be? So if we're labeling according to the angles, our options are right, acute, or obtuse. So let's take a look. Angle FBC is an inscribed angle. It is a right angle because it intercepts a diameter. So here we have 180 degrees. Half of that's 90. Once again, if it's an inscribed angle that intercepts the diameter, it is a right angle. I'm gonna put it here. It is a right triangle. An inscribed angle that intercepts a diameter is a right angle.